The objective of this topic is to give you a working knowledge of how heat and carbon change the mechanical properties of steel, and to provide you with some guidelines for welding carbon steels. You'll learn that steel is made up of crystals, called grains.
You'll see how heat affects the relationship between iron atoms, which are the basic building blocks of all steels. How steel transforms from austenite, which exists at elevated temperatures, into ferrite and pearlite when enough cooling time is available for carbon to diffuse. How a brittle structure called martensite forms when you let medium and high carbon steel cool too quickly, and how you can use heat to control cooling and return ductility to embrittled steel.
You'll learn how to use an SAE-AISI number to determine the major alloying elements and carbon content of steels, and how to read the AWS filler metal designation, so you can match filler metal to the steel you're welding.
From your own experience, you know that welding, the localized heating and cooling of metal, causes distortion, and that the amount of distortion is related to the rate of thermal expansion and the thermal conductivity of the metal you're welding, and that if you're not careful, welding can cause cracking. We're going to look briefly at the reasons that distortion and cracking occur in steel, and those lie deep within its very structure.
In its simplest form, steel is an alloy of iron and carbon. Carbon gives steel mechanical properties like hardness and strength, and it only takes a little carbon to do the trick. Most commonly welded steels contain up to 0.3% carbon by weight. That's not very much. Steel contains other alloying elements besides carbon, like manganese and silicon, along with impurities like sulfur and phosphorus that come from the steel-making process. But carbon has the biggest effect on weldability.
Molten steel solidifies by forming crystals called grains, just like water starts to form ice crystals when the temperature reaches 32 degrees Fahrenheit or 0 degrees Celsius. As the grains grow together, they form irregular boundaries where they meet.
Each grain is made up of millions of iron atoms arranged into cubic microstructures called space lattices. At room temperature, the iron atoms are arranged in a body-centered cubic, or BCC space lattice.
Carbon is soluble in iron, and carbon atoms are smaller than iron atoms, so they occupy the space, called interstitial space, between iron atoms. As the temperature increases to a critical point, called the transformation temperature, the space lattice changes from BCC to face-centered cubic, or FCC. And when it cools below the transformation temperature, it changes back to a BCC space lattice again. This ability to change from one type of microstructure to another is called allotropy.
Above the transformation temperature, steel is made up of grains of austenite with a face-centered cubic microstructure. Austenite is non-magnetic, and it can hold up to 2% carbon by weight in solution.
Below the transformation temperature, steel exists in the form of ferrite and pearlite. Pearlite grains consist of alternating layers of ferrite, which is very ductile because it's very low in carbon, and cementite. Cementite is high in carbon, so cementite is very hard.
The FCC lattice of austenite has more space available for carbon than the BCC microstructures that form below the transformation temperature. That means that the phase changes that occur during heating and cooling require the diffusion or movement of carbon, and diffusion takes time. So let's see what happens to carbon steel when there's enough time for diffusion to occur.
To simplify matters, we'll limit our discussion to steel with less than 0.8% carbon by weight, since you'll seldom have to weld on metal with higher carbon content than this.
Just like water transforms to ice as the temperature drops below 32 degrees Fahrenheit, or 0 degrees Celsius, so too austenite must start to transform into bodied-centered cubic microstructures when it drops below the transformation temperature.
But unlike water, the transformation temperature for steel varies with carbon content. For example, if the carbon content is 0.02% or less, the transformation temperature is 1670 degrees Fahrenheit. But as the carbon content increases, the transformation temperature drops to as low as 1333 degrees Fahrenheit at 0.8% carbon.
Below 0.8% carbon, ferrite starts to form along the grain boundaries of the austenite. Carbon has very low solubility in ferrite, less than 0.02%, so the excess carbon diffuses into the untransformed austenite. The process continues as the temperature drops, creating islands of carbon-enriched austenite, surrounded by ferrite.
When the carbon content of the austenite reaches 0.8%, it transforms to pearlite, which is made up of alternating layers of ferrite and cementite.
But remember that diffusion takes time, so if you cool austenite too quickly, there's no time for the carbon to diffuse. It gets trapped inside the space lattice as the austenite transforms, resulting in a distorted, body-centered lattice called martensite.
Martensite has an acicular or needle-like structure. Martensite is very hard and very brittle, and the higher the carbon content, the harder and more brittle it becomes. The rapid cooling that causes martensite is called quenching. Quenching occurs when you dip steel into a quenching medium like water or brine immediately after welding it.
Quenching also happens when the heat of welding is conducted away too quickly by the surrounding base metal, especially on thick sections, and when martensite forms in the weld or in the area around the weld called the heat-affected zone, it can result in cracking.
When you weld on carbon steel, several things are happening. First, the base metal under the arc is exposed to temperatures above 3,000 degrees Fahrenheit and becomes molten. Second, the heat generated by the arc is transmitted to the metal surrounding the weld, called the heat-affected zone, or HAZ.
For example, the area immediately next to the weld doesn't get hot enough to melt, but it does get hot enough to form austenite. And once you have austenite, you have the potential for trouble if you let it cool too quickly.
Third, when you're welding, the heat source is moving. So, as the metal under the arc is melting, the metal ahead of the arc is picking up heat, and the metal behind the arc is freezing to form the weld.
For a time, as the molten metal starts to cool, it transforms to austenite. And when you have austenite, you have the potential for trouble. Why?
Because if you let austenite cool too quickly, the carbon doesn't have time to diffuse. And why is that such a problem?
Because you end up with martensite, and martensite is brittle.
So, in most cases, when you're welding on carbon steel, you want to prevent martensite from forming, and the best way to do that is to control the rate at which the metal cools.
Steel is classified as low carbon, medium carbon, or high carbon, based on carbon content. Low carbon steel, like the steel used to make nails and welding electrodes, contains up to 0.3% carbon by weight. Medium carbon steels, like the steels used to make gears and crankshafts, contain between 0.3 and 0.6% carbon by weight. And high carbon steels, used for dies, cold chisels, and springs, contain between 0.6% and 1% carbon.
In general, low-carbon steels are easily welded and usually require no special heat treatment, with the possible exception of thick sections and weldments with high joint restraint, because low-carbon steel doesn't have enough carbon to form martensite. However, medium and high-carbon steels have the potential to form martensite if you let them cool too quickly. The tendency of a steel to form martensite is called hardenability.
Preheat is one way to control cooling. Without preheat, the cold metal surrounding the weld area acts like a heat sink, conducting heat away from the weld as it freezes. This causes the weld to cool too quickly and may lead to the formation of martensite, which in turn can cause cracking in the weld and in the heat-affected zone. But when you preheat the base metal, the heat of welding has no place to go, so it stays in the weld, allowing it to cool more slowly, which reduces the chances of forming martensite.
On some metals, you have to maintain proper interpass temperatures. You can use a pyrometer or heat-sensing crayons to monitor temperature throughout the welding operation. Another way to control the cooling rate is through post-weld heat treatments like annealing, normalizing, and stress relieving.
Annealing produces softness and high ductility. The weldment is placed in a special oven and the steel is heated into the austenitic range. Then it's left in the oven or placed in an insulated container to cool very slowly. Vacuum ovens are commonly used for annealing because they prevent problems associated with exposing hot metals to the atmosphere, like scaling due to oxidation. And vacuum ovens provide better control of mechanical properties because the cooling cycle can be programmed into the oven.
Normalizing is similar to annealing, but the weldment is allowed to cool in still air instead of in a closed oven. Since air cooling is faster than oven cooling, normalizing produces a finer grain structure with greater strength and less ductility than annealing.
Annealing and normalizing are useful because they allow you to alter the mechanical properties of the metal as well as relieve stress and eliminate gases that may be trapped in the weld.
Stress relieving takes place below the transformation temperature. It's used primarily to relieve residual stresses from welding and to return ductility to the weld and to the heat-affected zone.
Induction blankets are often used for stress relieving, which involves raising the temperature of the weldment between 900 and 1250 degrees Fahrenheit, or 480 and 680 degrees Celsius, and holding the temperature, usually for about an hour per inch of thickness, and then allowing it to cool.
You also have to take the history of the metal into consideration because prior welding and heat treatment can change the grain structure and mechanical properties of the metal.
The American Society for Testing and Materials, ASTM, maintains a series of specifications for a variety of materials. Each specification has an alphanumeric designation. The letter tells you what type of material it is. For example, the letter A stands for ferrous metal. The number identifies the specification to which the material is made. So, if you want to know the chemical composition of A36 steel, you'd have to look up ASTM specification A36.
But there are a couple of designation systems that are much more helpful to welders because they identify the chemical composition of the metal. The most widely used designation system for carbon and low alloy steels was developed by the Society of Automobile Engineers and the American Iron and Steel Institute. The 4-digit SAE-AISI designation tells you almost everything you need to know about a particular steel in order to weld it.
The first two digits tell you the major alloying element. For example, a 10 means that the major alloying element is carbon. The second two digits specify the amount of carbon. If the last two digits are 10, the steel contains between 0.08 and 0.13%, or about 1/10% carbon by weight.
So, in the SAE-AISI numbering system, the numbers 1006 to 1027 indicate low-carbon steel. Medium carbon steel is 1030 to 1050, and 1060 to 1095 designate high-carbon steels.
That means when you're welding on steel with an SAE-AISI number of 1030 or higher, you have to decide what kind of heat treatment to use, and you should figure this out before you start welding. Another useful designation system is the Unified Numbering System. The UNS designation for an alloy consists of a 5-digit number prefaced by a letter. The UNS system is very similar to the SAE-AISI system. For example, the UNS designation for SAE-AISI 1020 steel is G10-200.
The American Welding Society has developed a classification system for filler metals, so you can match the filler metal to the base metal you're welding. A typical AWS classification for carbon steel filler metal is ER70S-3. This classification covers gas metal arc welding, gas tungsten arc welding, and plasma arc welding, or PAW.
The ER stands for electrode or rod. If you're welding with GMAW, the E applies because the filler also delivers current for the arc. And when you're welding with GTAW or PAW, the R designation applies because it's used for filler only.
The two digits after the prefix indicate the minimum tensile strength of the deposited weld. A 70 means that the deposited filler metal will have a minimum tensile strength of 70,000 pounds per square inch.
The S means that the filler metal is solid, and the suffix indicates the chemical composition of the filler metal. The rule of thumb for selecting filler metal for carbon steel is to match the tensile strength and the chemical composition of the base metal as closely as possible.
So, steel is an iron-carbon alloy, with other alloying elements added to achieve specific mechanical properties.
Iron is allotropic. Its atomic space lattice changes from body-centered cubic to face-centered cubic at a critical temperature called the transformation temperature. The transformation temperature varies from 1670 degrees Fahrenheit at 0.02% carbon to 1333 degrees Fahrenheit at 0.8% carbon.
Carbon is soluble in iron and occupies the spaces between iron atoms. The The transformation of austenite into ferrite and pearlite requires the diffusion of carbon, and diffusion takes time.
When austenite containing medium to high amounts of carbon cools too quickly, there's no time for diffusion to occur, and the austenite transforms into martensite. Martensite is hard and brittle, and it can cause cracking in the weld and in the heat-affected zone.
So, when you weld medium and high carbon steel, and even when you're welding thick sections of low carbon steel, you have to control the cooling rate with preheat, post-heat, or a combination of both.
As long as you know the SAE AISI number of the steel you're working with, you can determine its major alloying element and its carbon content. And you can use the AWS classification system for electrodes to match the filler metal to the base metal you're welding.
A good welder also takes the fabrication history of the metal into consideration, because prior welding and heat treatment can change the grain structure and mechanical properties of steel.